So impulse and momentum, probably the best way to think about this. Let's see, last time we talked about work and energy, which considered distance. In other words, you lift something and it's a question of like, okay, well, that's great. You lifted 100 pounds, but there should be some credit given for how far did you lift it? Remember that concept? So somebody says, well, hey, let's invent this idea of work that will not only talk about the force, but also the distance that you carried it. And so work will include that. And then energy turned out to be the same exact units. And so again, that's kind of neat to think, oh yeah, energy and work. Do I have the energy to do the work that I need to do? The fact that those are kind of related or even identical, kind of cool. So that's a cool concept. Why did somebody invent something called impulse? I'll write this down in a little bit, but it has to do with, well, let's consider force, but this time not as a function of distance, but as a function of time. So for instance, if you're playing baseball, I'll talk about this in detail in just a minute, but it's like, here comes the ball, boom, I swing around with a certain amount of force. If I got muscles and strength, that'd be good because I'll be able to hit it further. But it's not just force, it's like how much time does it contact you? Even better example is like what airbags do in a car. So another car comes at you with a whole bunch of momentum and force, and it's gonna hit you. And so, okay, great, that's thousands of pounds of force, if you will. But the question is, how long does it spend forcing on you, if you will? Well, the idea of an airbag is to increase that time. Think of it as like you're gonna just hit a wall, like it's not another car, but you just drive into a telephone pole. I've got all this force that my car is generating and I'm flying down the road and I hit the telephone pole. The reality is I'm going to come to a stop now. And so if you can come to a stop in 0.01 seconds, that's going to be really hard on your internal organs to sort of stay where they belong, and your head and windshield, all that kind of stuff. And so the main purpose of an airbag is actually to bring you to a stop, but just tripling the time. If it triples the time, it's going to cut the force by a third. Does that make sense? It was 10,000 pounds. And you made the time 10 times longer by slowing you down with an airbag. And so now you have 10 times less force to absorb. And so it's the same concept as like catching an egg. Just hold your hand, it goes, you go, and try to make contact with it slowly. So that's the idea behind impulse and momentum. So just like energy and work were analogous to each other, in this section, we're going to talk about impulse and momentum. So I'm sure you have at least a rough idea of momentum, like, would you rather be hit by a train or like a bird running into you? Well, it kind of depends on the speed. A train really slow won't hurt you, and a bird really fast will. So the automatic answer is not just bird. So, that's kind of what momentum is. Momentum is a force and a time. So here's a cool illustration. So this is the largest waterfall I have ever run, called Big Brother. And I just want you to kind of pay attention to what happens. This is a good video. Like, this guy doesn't, I like carnage videos better where somebody just gets worked, but this guy does pretty good. It'd be fun just to kind of watch the whole thing, but I'll just go ahead to where he actually gets into the water. Think about what happens when he hits down there. Hasn't he built up lots of momentum, falling through the air, all this force pushing on him? But then, of course, when he hits the water in the bottom, it's going to come to a stop, right? No different than crashing your car into a pole. So let's think about one thing really quick. If I'm in my kayak like this and I go off a waterfall and I land flat like that, how's that going to be different than if I go off and I rotate my boat forward a little bit? What's going to happen when I land now, because I'm kind of at an angle like this? Yeah, does it make sense? It's going to like shoot into the water a little bit more. That's exactly the idea of an airbag. What you don't want to do when you go off a waterfall 25 feet high is land like that. This room is only like maybe 12 feet tall, like double that. I pushed you off that and you landed. And if you land in hard water, green water, it's going to be pretty close to landing on the floor. I mean, it's going to stop you just like this, but you're not going to sink very much. Now, unlike this, you will sink a little bit, even if you land flat, but obviously when I ran this, I tucked my head forward like this and my head just went thump on the boat because I landed pretty flat. Going off of that, my neck was sore for a couple of days as a result of that. But kind of watch the angle that this guy goes in at as we're sort of playing around with this. So that's a couple of shots from a distance. Now this is a head cam. Thought I was scared shitless when I was right there. But does this boat look flat or does it look angled? It's kind of some combination of them, wouldn't you say? It was like, you went in the cave on the right, which is not where you want to go. This is a second run, not just another shot. Oh yeah, it is. Did you see that one a little bit more of an angle? But he still went in the cave, which kind of sucks. But I mean, that's what we're trying to quantify here is, how do you take into account the fact that I've got a force, gravity's pulling on me for a certain distance, and so there's a bunch of kind of force built up. And notice it's starting to feel kind of confusing. It's feeling like physics started to get confusing, like we have work and energy and gravity and all these things. Starting to feel like, I'm swirling around a little bit. So you definitely want to be paying attention to notes here and so forth. But the idea that time is a factor in this, if that water could catch him like you catch an egg and just like slowly bring him to a stop, and be like, this is perfectly nice. But landing flat, as I said, in hard water, green water, if you shoot out from the falls far enough that you don't even land in that white aerated water, because that's pretty soft when you land in that. But if you just land in flat green water like lake water, then it's just like landing in a rock.
So that's true then. So like we see people doing cliff jumps, like throw a rock off the top first, like break the surface.
Oh yeah.
Yeah, that's exactly right. That's exactly right. So you either need to go in like this so you don't stop much, but if you land flat, and you jump off a 60-footer, you're probably going to get genuinely injured from that, or 50 or whatever. But people have broken their backs off this. Guys died off that waterfall. It's 25 feet. That's not a joke. You watch a movie like that and it's a video and the guy's like, yeah. And then, most guys that run it, everything goes okay. But it's like, you get that wrong, land in the wrong spot where there's rocks on the side. Again, rock is just like hard water, except it's actually not going to move. So so ultimately impulse is a force with consideration of time. Actually, it doesn't matter how much force is, as long as it slowly impacts you, if you will. So anyway, it's kind of a cool concept. Let's see if we can make progress. Let's see, now that I've put that screen on there, does this, if I share this screen, do I get, does it switch or not? Turn that off. Let's rid of this. I haven't done this before. Get this to be the projected item. Guess I'm going to try turning it off and turning it back on. Okay, so while we're sort of screwing around here, take a look at your note sheet if you have it, in terms of what formulas do you have to look at? Okay, so impulse is a force times a time. And let's think about what that would be. Okay, so if it's force in consideration of time, force times a time, so a small time would decrease the impulse, a tiny time would decrease the amount of impulse. A large time would increase it. Let's think about that. Well, what would the units of this be? Is that coming alive yet? Why is it taking so long? So we know that force is newtons, or I guess more, I don't know, somewhat more clearly, kilogram meters per second squared. What's going on with that thing? Let's try again. And time, of course, is in seconds. And so I'm going to begin writing, even though you can't see this yet. So in force is kilogram meter per second squared, and then time is in seconds. So what would the unit then of impulse be? I have kilogram meters per second squared, but then times seconds. So that gets rid of one of the seconds. Seconds cancel. Yes, it's finally on. So do you agree then that this second cancels with one of those seconds, and so we're left with kilogram meters per second, kind of as a unit? Or couldn't we have just said, well, forget all that cancellation stuff? Like, isn't that a Newton? So wouldn't the units just be Newton seconds? Kind of like work was Newton meters, force times the distance. Well, this is just a force times the time, so wouldn't it be Newton seconds? But if I kind of do the cancellation right there, do you see I get kilogram meters per second? What would that, what are those? Like written the way that I have it here, the unit is Newton seconds. So it's kind of like work, except for, well, impulse, it's got time involved. But kilogram, if it's kilograms and then meters per second, what are those? What is kilogram? What's kilogram? What quantity is that? What is meters per second? What quantity is that? What is it? What's a watt? I forgot. I'm actually going to look with you when you say that because I'm not sure. Yeah, it's close. A watt is a Newton meter per second. Not Newton seconds, but Newton meters per second. So it's more complicated than that. More simply, do you agree that a kilogram is just a unit for mass all by itself? And what's meters per second? Yeah, it's a distance over a time, which is a velocity. And so really in this form, this is the sort of momentum form. Just like in the last, this is very analogous to what we did before, in the sense that in one form we said, oh yeah, it's energy, but then in another form we looked at the units and said, oh, that could be reconfigured to be a force times the distance, then we'll call it work. And so work and energy were the same thing. Well, here, impulse measured in Newton meters, or Newton seconds, I'm sorry, impulse measured in Newton seconds, and momentum measured in kilogram meters per second, those are both the same exact term. So momentum and impulse are kind of the same thing. Again, those don't feel very good though, right? Now, again, momentum probably feels decent to you from physics because a train has a lot of momentum. It's very hard to stop a train, even if it's moving slowly, because it has little speed, but it has just so much mass. So, you know, that's a nicer version of this. I think impulse doesn't feel near as good as momentum does. I got a mass and a velocity together. Those sort of work together to, I don't know, do work, smash into you, whatever. So you can see that a big velocity would have a lot of momentum, like a bird flying really fast. But a train, although a small velocity, has a gigantic mass. And so a bird and a train could actually have the same momentum. And that's the idea here. Just talking about mass is great. How much does a train weigh? How much does a bird weigh? Big, small, great. But if they're moving, all of a sudden, kind of that sense of how much damage can they do? How much energy do they have, so to speak? You know, what do we want to quantify that as? So, I mean, that's the idea here is that somebody said, well, you know, that's kind of a thing. Like we need a term for that. So momentum is really it, and impulse can be the same thing. Momentum, though, just looks at it in terms of more, as I said, more naturally, I think, is a mass and a velocity, whereas a force and a time is impulse. And again, the reason I showed you the kayak thing is in the kayak example, it's really a force and a time. I have a certain amount of weight. I land on that water. If the amount of time it takes me to come to a stop can be increased, then I'm not going to get smashed quite as much is sort of the idea. So that's why they're related to each other. So I kind of like to think of this as like sort of like a strength or like strength or quality of motion. It's kind of my own language, just trying to make sense of it. Yeah, something's moving. Oh yeah, the car's moving. But you know, how do I put numbers to that? Well, the fact that it weighs something and is going at speed matters. So it's kind of a measurement of its strength or its quality of motion, I guess you might say.
So
How's that grab you? Go ahead.
is impulse in kilograms per times meters per second squared or the same as momentum?
Yeah, I mean, if you cancel the units, because collectively here, a force is kilogram meters per second squared. So this entire thing is just a Newton. And then times a time, which is in seconds. And so if I say, oh, look, I'm multiplying by seconds and this was dividing by seconds, then I can get rid of those. And then it ends up kilogram meters per second, which is sort of the way you think of momentum. But if you just leave it alone and say, well, you don't even write that as kilogram meters per second squared, just write it as a Newton. Well, then it's Newton seconds, like there wasn't any cancellation. So impulse is Newton seconds and momentum is kilogram meters per second. They're the same exact unit.
Okay, so
Which
you're
is kind of
basically dealing with
force and time.
or force and time.
Yeah.
Or, but I'm saying like with impulse, you're dealing with a force. With momentum, you're dealing with a mass.
That's exactly right. So over here, impulse is really kind of like force and time. I probably should put that sign because it makes it look like it's division. But this is a force and time where this is actually a mass and a velocity. But the units end up the same. Isn't that kind of weird? And of course, mass and force are kind of analogous, right? Mass just needs gravity, like you got to add gravity to it. And velocity's got time in it as well. So the ideas are analogous. Well, let's just kind of play. Let's play with this a little bit. I think the baseball example here will work really good. So I looked all this up online. This is actually accurate. So baseball. So if a baseball's mass is 15 kilograms, by the way, what I found online was actually 5 ounces, and then I just converted it to kilograms to get this. So 5 ounces is what a baseball weighs. But you know, its mass version metric is kilograms. And so, okay, that's cool. So here's this ball, and let's say the pitcher throws it at a velocity of 40 meters a second. Again, neither of those two units speak to me. I don't know about you guys. You're probably better at metric than I am, but when I hear that, I think, is that realistic? Was that like if somebody throws a pitch? You guys know anything about baseball? Anybody like baseball? What's a fast pitcher in baseball? 90s, yeah. Pros, 90s. If you get a high schooler that throws 90s, it's probably going to strike out. 15 of the 21 outs. You know, it's like it's really hard to hit 90 miles an hour. 40 is 90 miles an hour. So this guy's an, you know, the best high school pitcher in the state, or a garden variety pro pitcher. So regular baseball thrown in at that much speed. Okay, cool. So does it make sense that's the quality of their pitch? It's not just how fast they threw it, because what happens if he throws something in and it weighs like 50 pounds and the, you know, it's like a super dense, you know, fake ball, like a pool ball or something, and the batter, you know, goes like this. What's going to happen? The bat's going to snap off. The guy's going to break his wrist. The ball's going to like make it to the pitcher. Does that make sense? So the mass is a part of the quality of the motion of that ball, right? So is the speed. Okay, cool. So, you know, boom, here comes the ball. Whoosh, whoosh, whoosh. And notice, if you multiplied those together, wouldn't you actually get a measurement of momentum? And so, you know, the idea of multiplying them in a sense is only necessary just to kind of make one number out of it. And that's why somebody thought, well, let's come up with this thing called momentum, and we'll just combine those two numbers together. And notice they're not divided this time, they're actually multiplied, because, you know, each one being bigger causes the overall momentum to be larger. If I have a bigger speed or a bigger mass, then that's just going to make this, you know, more momentous, if you will. So that kind of feels right that they're multiplied, doesn't it? Because remember, some of our other formulas, we were dividing by time, and sometimes we multiply, sometimes we divide it. So here comes this ball cruising in. Okay, great. Well, of course, it's on the way to a bat. We'll draw a Fred Flintstone sort of bat, since I lack the, does that look more like a bat, or is that a chicken leg? It's a drumstick. I'm such a failure. Well, what does the batter do? Interestingly, so do you agree that it was, if you will, natural that the baseball had momentum? Interestingly, the bat actually ends up with impulse. Like, what does the bat naturally do? Well, you could say it's also got a speed and it's got a weight, which is kind of true. But the reality is you swing with a certain amount of force based on how muscular you are, a certain amount of force, and then you're going to contact the ball for a really short period of time. So it's going to hit the bat and then be sort of sent back in the other direction. Also looked up some of this a little bit. Let's say that this is being swung, this chicken leg is being swung at the ball with 22,500 newtons of force. And again, for me, that means absolutely nothing, but that's actually about 5,000 pounds. So I did go to a baseball site and try to figure some of this stuff out. So 5,000 pounds of force, that doesn't mean that person can bench press 5,000 pounds. So that kind of bothered me a little bit. Like, what does that mean? You know, it's like, I can't lift 5,000. It's like, what is that? Is that some combination of, like, you know, swing speed and so forth? Because remember, you could think of this as, you could do the same exact thing. How much does the bat weigh in mass, and how fast is the person swinging it? Does it make sense? You could say momentum equals momentum here too. You could absolutely do that. What do you think about time, though? How much time would you think that a bat is in contact with a ball?
Very milliseconds.
Yeah, less than a second, obviously.
So when the aluminum bat gets the ball further, and it wouldn't, it's in contact with the ball for less time.
Yeah, the ball actually does fold around the bat a little bit if you see it in slow motion, because it's such a high. Same with the golf ball. Like, if you see the slow motion, the golf ball actually flattens out, and that if you have a really good time-lapse camera shot of it. Turns out that's kind of what I found on the internet. Notice it's, let's see, we're good enough to do this. That would be 0.7 milliseconds, wouldn't it? Milli is 1,000. Am I doing that right? 1,000, like a millimeter. Yeah. So that's less than 1 millisecond. So anyway, that's what I found online. So, okay. What does that all mean? Well, here's kind of what this all comes down to. Just like in the last section, we said, if you take a certain amount of energy plus a certain amount of work, that's going to be conserved. We have the same formula in our section right here. In other words, you have an initial, let's see, what would that be? You tell me. What's an initial what? based on it's an initial mass times velocity, which is momentum, right? So it's got an initial momentum plus a force times the time. Since these two things are analogous, basically you have an impulse and a momentum. So you have the impulse, let's see, did I say this right? You have the momentum of the baseball plus the impulse of the bat. And does that word at least feel a little bit better when you call it impulse? The bat goes whack, that's not so much of it could be thought of as a momentum for sure, but it's kind of an impulse. The idea is it's a pulse. It's like a quick blast. You're doing something to it. Same thing with the kid on a swing. The kid on a swing flies towards you and they got a certain mass and velocity, and then you go poosh, and then you kind of add to the program. I mean, does that equation make sense? Does that feel analogous to the energy and work concept? You have a certain amount of momentum, and the implication behind impulse is tiny time. Like there's no such thing as an impulse of 3 hours. It's always tiny times. It's something that you do, boom, the car hits the pole, boom, in 1 second, everything has changed. Has a certain amount of momentum, you do something to it, and then things change. So I do that, and then ultimately momentum will be conserved. Notice there's no impulse in the other side of it because that's over. You had a momentum, you did something brief to change it, either like a kid on a swing, hopefully they're going away from you when you push them, right? What happens if the kid's swinging towards you and you push them? The neck snaps off. And that's what we're gonna do with the baseball, right? It's gonna come toward us and we're not gonna it's coming this way. We're not gonna help it keep on going. We're gonna send it in the opposite direction. So does that have at least some decent feel to you? I mean, you got, formulas that we're going to use, but I'm always into does this stuff make any sense?
But would it be positive? Because they're both fighting against each other.
Yeah, that's exactly right. Now, it is like with the kid on the swing, they have a certain amount of momentum going away from you, and maybe we'll call that positive. Remember, it's kind of like, which way is positive on a swing set? I don't know. We'll call that way positive. And then you add an impulse in the same direction, and so that's going to increase their momentum. Does that make sense? Whereas these are kind of fighting against each other. It's like I got momentum going this way, and then I got an impulse going the other way, right? So it's kind of like, do I add those, or see what I'm saying? Do I have to call one of them a negative? Does that feel a little like, I'm not really sure what to do there?
With energy, we don't deal with direction though.
Yeah, that's exactly right. And that's why this is kind of confusing, is that a certain amount of, in a sense, energy doesn't really care what direction the velocity is going. So this doesn't feel very good to me either. But let's at least start, plugging some things in here and thinking about it anyway. So we said the baseball had a mass of 0.15. I got all the units up above, so I'll just leave them out. Had a velocity of 40, and so I could multiply those two, and I have a certain amount of momentum for the baseball. But then I've got this force, which is in the right units, 22,500 newtons. And I've got a time of 0.0007 seconds. So yeah, I mean, this bothers me a bit. What do you think? Should something be negative there? Or is it? I mean, is it going to have more momentum than it had before? Seems like it would, because the impact is pretty major here. This isn't a tiny impact, pretty major impact. The force is going in the opposite direction though. Didn't we say that mattered with respect to work? Like the force and the distance kind of had to be going the same direction. Do you think it makes more sense to, because you can't say negative time, right? The only thing that really could be negative is force, because it's kind of pushing in the opposite direction of the baseball. So in the end, we're kind of going swoosh with our chicken leg. And the answer is, yeah, that's exactly right. I mean, these are going in opposite directions, because if the ball came past me, as I showed you a minute ago, if the ball came past me like this, and it was flying along doing just great, and then I came behind it like this and went whack and hit it even harder, shouldn't that be different than if it came this way and I said, no, you got to go the other way?
Somebody hits a baseball going faster than somebody threw it.
If you do home runs, that's one.
Mhm. Well, the baseball hasn't changed its size. So does it make sense that actually allows you to figure out the velocity of that the baseball is going to end up with? So in a sense, that equation is getting at horizontal or conservation of momentum. What does your note sheet say about that? Let's take a look at it. So everything I've discussed here, in a sense, is kind of written in this first part, but we're using that equation right there, which is kind of the big takeaway equation. It's using the ingredients of momentum and impulse. They're both a part of this. Notice, what does that sum mean right there? It actually means there could be more than one impulse happening to something, which doesn't make sense in baseball. There'd just be one, but a car crash there would, right? You smack into one car and then you smack into another car and a bunch of impulses happen. So yeah, you could get hit more than once. But of course, what's that saying? That's saying the initial momentum plus whatever impulse or impulses you have is going to give you kind of a brand new momentum. And it might be faster, it might be slower. And as I said here, I think that's important in order to kind of make any sense of this, just like working energy, except we're talking about time, not distance. So we got formulas, but we want to have some sense of kind of understanding. Well, cool. If I solve that for velocity final, I actually do indeed get a negative number. In one sense, there is not any such thing as a negative velocity, but the negative is telling you what direction it goes, right? It's going the opposite direction of what it came in at. Interestingly, notice it's going faster than it came in at in this case. It's coming in at 40, which is 90 miles an hour, and it went out, whatever that conversion is, over 100. So just to reiterate one thing, I think it's important to think of everything as having some momentum. Well, at least if it has some velocity. So that's the established number for something. Hey, look, there's a car driving down the road. It's got momentum. It's got a weight. It's got a speed. But then stuff can happen to it in a brief second. You can hit the brakes really hard. Isn't that an impulse? Boom, hit the brakes really hard. Boom, hit a bird, hit a tree, and stuff like that. And so this, I can see why this exists. I mean, that's kind of where I want you to be now. Let's see, did I already load stuff in here or not? Looks like I did not. So let's take a look at that first problem that you have that is exactly a picture, because I'm just trying to give you time to soak this in a little bit. Can you figure out Big Brother? This must be 15.2. Yes. So this is a way more interesting question than any questions in the book. So 25-foot falls. What's involved in taking the hit at the bottom? So as you fly through the air, you're a speed and you're a mass, and then you're about to be impacted by the water. So we just want to think about, like, what's that going to mean? Does it make sense? What's interesting about this is that I'm gonna have to absorb a force when I land. It's kind of like the water's about to be pushing up on me. And again, you can appreciate if that's a small force, and I won't really notice it. But if it's a big force, I might break my back. My back won't be able to handle that. So let's just play around with this a little bit. So I'm kind of, I'm roughly thinking something like, well, what we just did. I'm thinking, what would my initial momentum be? What was the force times the time of the impact? And then what will happen when I'm finished? Well, just to start with, does it make sense that in this case, your velocity final will be nothing? Like you come to a stop, you hit the telephone pole, and you're not moving anymore. Your mass is your mass, whatever you weigh. Some forces involved. Is there any way to know anything about this? It would make sense that you'd have to kind of weigh yourself, right? So we could make up some number for your weight. how much does a kayaker weigh? Well, you know, this is somewhat real to me. Like I weigh 170 pounds now, which unfortunately is a force, not a mass, right? So if I divide that by 32.2, force divided by acceleration will give me a mass, except for what's wrong with that calculation? I said I weigh 170. What's missing from that? The boat, which weighs 40 pounds. So it's really that. So if I punch that in for my, so I can know that. Does that make sense? That'd be my mass. That's not just some made up number. Like I know how much I weigh. I know how much kayaks weigh. Going to Mill Creek after work again tonight, so I got to carry that stupid thing out. So I know that. So that's kind of cool. I won't even calculate that right now. I'll just throw it in over here. Do I know my velocity? I just have to make that up. This is a great problem because it's so big picture. Like I know I'm going to fall 25 feet, don't I? Shouldn't I be able to figure out? We've worked with projectile motion kind of stuff. Again, I would, in this context, that feels kind of challenging, but didn't we have the S of y equation? The distance in y is 1/2 times the acceleration in y times time squared plus the initial velocity in y times time plus the initial position. Like that's what told us the relationship between position. And notice I chose that one, not the velocity equation. I chose that because I know how high I'm falling and I got to get 25 into this or I'm not going to be able to make any progress. Yeah, so don't I know a lot of this? So there's more than one way I could say this. I could say my position in y initially is 25 feet. And then when I land, I'm at 0. And that would be if I decided to call the ground 0. Does that make sense? So I could call the takeoff 0, and then I'd land at 25 feet negatively. Those would both be the same.
Will your acceleration be more than gravity though, because the water pushes down?
No, because this is all flying through the air. See, what I want to know is how much momentum I have, like right when I hit. So I'm flying through the air. I haven't touched the water yet. As soon as I touch the water, now it's impulse. Now I got an impulse acting on me. So it's kind of like how much energy, how much emotional power do I have, and the word do I use for that? So no, that actually hasn't changed. That's still. So yeah, reason with me about this. Like ask questions. What's my initial velocity? If I basically decide to make this 0 up here, then what's my velocity when I'm up there initially? What's my downward velocity? Nothing. Guys, I haven't fallen yet, right? So I started at nothing and I'm going to fall 25 feet. And I'm just interested to know what my velocity is later. So I plugged in everything. Do I like what I have here? Well, let's see, what does that is? 0 equals 32.2 be 16.1 t squared plus nothing t plus 25. Oh yeah, that's an equation I can solve. I like equations with only one unknown. This is going to tell me how much time I fell. Well, that's kind of a bummer. I didn't really want to know how much time. I wanted to know my velocity because this isn't the time for the impulse. The impulse is going to be really brief. That's the water. This is going to tell me how much time I fell through the air. So if I punch that, I get 40 point, no, I don't know what I get. I better just do it. I'm looking at my notes, but I don't see my answer to that. Nice catch. I was just staring at that equation thinking, isn't this not going to ever be equal to 0? Everybody see that? Like I was staring at it thinking, if I have something squared plus 25, it'll never be equal to 0.
What happened to your other t?
This t went away. This t went away because it was being multiplied by 0. So yeah, Tristan saved us because this is not positive that gravity is not sending me up in the air, right? Sending me down. So this should be negative. So that was a mistake on my part. So if I take 25 divided by 16.1, 5 divided by 16.1, and then I square root that, I get 1.25 approximately. Largest waterfall ever caught, 186 feet. Does it make sense? It would be good to know how much time in that particular waterfall too. There's the dude was kind of in the water and you couldn't really see. Does it make sense? It'd be nice to know when you're going to hit, because then you can kind of prepare yourself a little bit. Maybe before then you should be doing stuff like trying to land correctly, and then when it's time to hit, if you can see the water, then fine. Then you can be like, oh, there it is. And then you, ideally in a kayak, you actually tuck yourself forward so your back doesn't take all the strain. And so the paddle doesn't hit you in the face and all kinds of bad stuff. But does it make sense? It'd be kind of nice to know. So in my case, I could have calculated this ahead of time and said, oh, I got about 1.25 seconds, 1/1000, bam, I'm going to land. It's kind of cool to know that. But that's not really what I wanted to know. There's no place for me to plug that in. But remember, our second equation said, let's see, what was it? V, the velocity in y is equal to the acceleration in y times time plus the initial velocity. Is this it? Is that what it was?
Yeah.
So that does help me. Our initial velocity in y is still nothing. Our time we just figured out is 1.25 seconds. Our acceleration in y is negative. Thank you. 32.2. Oh, okay. So if I just multiply 32.2 times 1.25, that number is still sitting in my calculator. So if I say times 32.2, I get velocity in y is 40 point whatever, 40.1. Does it make sense? That's at 25 feet, which basically means right before I hit the water. So I'm at that point in time, I'm just flying through the air. I've got 210 pounds of force. I've got 40 meters a second. Wait, I'm all screwed up here. This isn't meters a second. This whole thing has been in feet. Have I screwed anything else up? This is feet. That's it. I got 210 pounds of weight, and now I've got 40 for velocity. So I got weight and velocity. I got a lot of momentum, right? So whatever I ran into, man, I'm going to smash it. If this is football, this is great, man. I'm going to hammer this, but I'm going to lose this fight. Does that make sense? I'm landing in rocks. I'm landing in water. Like, I'm not going to win this. My momentum as a football player versus somebody else's momentum. Okay, who's going to win? Who has the most momentum is going to win. But I'm going to lose here. Well, isn't that cool? Because now I actually know what my initial momentum is. Isn't that kind of sweet? If I go back up to the top where I was up here, I can say, bam, I actually figured out my speed entirely just based on the context of the problem and based on stuff that we already knew before. That's kind of cool. So I now have my initial momentum. By itself, that number doesn't really mean much to me. I don't, like if I say you have a minimum of 600, like I don't know what that means. That doesn't feel like a unit that I understand, you know what I mean? I wouldn't know what that means. But I understand if my momentum was more than yours, then that would be something good. Okay, cool. Well, do I know anything about force and time? Yeah. Isn't the force your weight? Well, the answer is no, because it's not, the impulse is not me, it's the water. Think of me flying through the air and the water's like, here he comes, you know, and I'm gonna do what the bat did. You see what I mean? So it's more like the force of the water pushing against you. So it's like the bat. So it isn't actually your force, it's not your weight, it's actually the water's. So I actually don't know what that force is. Now, the one thing on this I have to guess at is the time. So actually this equation is sitting here ready to solve. Notice the right side is equal to 0, thanks to the final velocity being 0. I don't care about the mass over there. I've just got a force and a time, and I don't know either one of those. I don't know how hard the water is going to push, and I don't know how long it's going to take to bring me to a stop. The only thing I have to guess at is the time. And again, that's totally dependent on how you land. If you land flat, it's going to be a really short time, which is going to cause there to be a lot of force. if you land at an angle so that you come to the stop as you plunge into the water and then finally come to a stop. Does that make sense how important that is? Then that's going to radically change the force. I'm guessing still less than a second. I don't know, just for the heck of it. Let's just make up the number 0.2 seconds. So that'd be kind of cool to video and actually watch a time lapse. Couldn't you watch somebody land that, do a little time lapse thing and figure out how much time that actually was, especially if you had a super, nice camera, if you will. Does it make sense now? We're actually going to be able, armed with that, we're going to be able to figure out the force that the water pushed on me. And of course, this is an important calculation because I'm about to decide if that's enough force to break my back. Does that make sense? So I'm just taking 210 divided by 32.2, multiplying that times 40.1. Got this big number, 261. And then I'm gonna, I guess, maybe I'll just go ahead and write this out. There's no reason we can't. I don't want to be in a hurry here, even if we don't finish. I got 261.5 for momentum, plus my force times 0.2 equals 0. So if I subtract that to the other side, negative force times 0.2, then I divide by 0.2, and I got 1,308. Except negative. Why did it come out negative? Yeah, because I was falling downward and the force, the impulse that happened to me sent me in the opposite direction, just like the baseball. It didn't come above me and make me go even faster.
Is that 130 or
1,300. 1,308. Yeah, lot, right? Huge. Does it make sense if you divide it by 0.4? That would have cut that in half. Now it's only 600 pounds. Do you see why it's so cool to increase the time? So that's why airbags exist. That's the principle right there. That's why as a kayaker, you don't want to land flat because you're going to have a tiny amount of time. Do kayakers know any of that? No, they just know that when they landed flat, it hurt. And it's like, let's not do that again. Isn't that cool? This is, again, I think that's a great illustration for what this is like. And so if I have to absorb 1,300 pounds of force, and think of it as just like, I don't know, bench pressing, that's a lot of weight. If you can bench press 200 pounds, you're doing good. Well, that's like 7 of those that dropped on you. Feels like, uh-oh, that's not good. But the good thing is it's going to last for 0.2 seconds and it'll be over. So can I absorb that much? Well, yeah, if I'm ready for it. That's kind of why you want to land a certain way. So I think that's a great way for you to kind of get a feel for what this is really accomplishing and why physicists invented this whole idea, because of the amount, because car crashes and things that, I don't know, you guys brainstorm, what else? Car crashes and, jumping like this, maybe a mountain bike crashing on the ground and that kind of stuff. Is there other things that occur to you guys that?
Thinking like taking a hit in football,
Yeah,
like how much force?
exactly. Taking a hit in football.
Probably a lot.
Yeah.
Force from a big line factor.
Yeah. Some pro that's 250 pounds that can run 4-second 40. That's a lot of momentum, man. Yeah, skiers jumping off cliffs.
Yeah.
You land. If you land on soft snow so that you get to sink for a while, you might be okay. But if you land on something kind of hard, not good. Let's see. Shall we look at next? In the interest of time, do we want to do that?
Still imagining how to build a crate with 1,300 pounds and you run straight full at it.
Yeah, let's go ahead and look at this one. We'll see what we do time wise, but. So this is a question I did before with you. You won't certainly remember this, but let's just consider this. I won't redo the way we did it before, but so this, this person is pulling their kayak at a certain speed. We're trying to reach a certain speed. They have 8 seconds and there's a certain amount of force involved. And so before we did this with the force equals mass times acceleration equations. And because the force I'm pulling on that little cord connecting it to my back there, because I'm pulling upward, there's like a vertical force component and a horizontal, and we sort of set up those two equations and we were able to kind of figure out, oh, okay, I see how much force I was on it and so forth, based on how much the kayak weighs and friction on the ground and all that kind of stuff. But let's just consider this, kind of reconsider this as an impulse momentum problem. So no different than a second ago, because I said vertical, then we're considering our velocity in y. That's our initial velocity. And we have forces and times, force in the y direction and a time. There could be a whole bunch of those. So I'm going to leave some space for it. I want you to think about that. And then I'll have my final velocity in y. So let's quickly draw a free body diagram of this. So if I'm pulling on this, don't I have the kayak sitting on the ground? We're told the kayak weighs 32 kilograms. And so I've got that force pulling it up at an angle, and I've got the force of the kayak going down to the ground. That's exactly right. And then the ground is going to push up. So this is like gravity, which would be mass times, let's see, this is all metric, it looks like. So that'd be 9.81. So that's gravity pushing down. Is that all the forces? So this is the force of me pulling against it, right? Is there anything missing in that?
Friction.
Yeah, there's friction. And do you understand where that would go? It's always going the opposite direction of travel. So since this thing's trying to go to the right, then the force of friction is actually pulling to the left. So, okay, I think I got it now. Okay, so with respect to what's going on in y, then what's really happening here? Well, does it make sense I actually have more than one force in y to deal with here?
Yeah.
I mean, I've got gravity. I've got the force of, notice the friction's not in y. That's an x, so I'll have to do an x. That's why I wrote vertical. I've got my force, which is in y, the force of me pulling on the kayak, and then I've got gravity pulling down on it and so forth. But notice this normal force of the ground right here. I don't actually know what that is. You understand that? Because it's not the same as gravity, because I'm taking some load off. Like if the boat weighed 80 pounds and it was just sitting there, then the ground would be pushing it 80 pounds. But because I'm pulling up on it, I'm actually helping a little bit. So the normal gravity is not going to be that much, is it? So unfortunately, I don't actually know what that is.
Do you know how much force you're pulling?
No, because this is saying find the force. So we don't know his force. So actually, it looks to me like, wow, there's a whole bunch of these. Maybe for now, I'll just, instead of writing them all out, I'll go ahead and write that sum symbol. And there's a whole bunch of those. And so, okay, let's just start figuring out what we got. Well, if I'm starting from rest, does it make sense you have no initial velocity? Again, does it have to be none? Could you have Did you already have some velocity? Sure. So I'm at rest. But I have a whole bunch of, so I have no momentum because I haven't started moving yet. The car's not moving. But then there's all these forces pushing on it in the Y direction, in different directions. And so I've got the normal of gravity times time. Do you agree that I'm just going to, in the interest of time, plug that in, plug 8 seconds, because this is all going to go down over 8 seconds. Notice that's kind of a long impulse, if you will. It's not typical for an impulse. As I said, it's kind of implies that it's going to be a short period of time. So I got that force pushing up. I've got the 32, let's see, what is 32 times 9.81? That is roughly 314. So I've got that 314. It's also acting the entire time, 8 seconds. So that's down. And then I got my force. But it's got to be modified by the sine of 38, does it not? And it's also acting for 8 seconds the entire time. Do you agree with that? So there's actually 3 impulses. I'll just write it in here. All impulses. It's kind of a good example of how something can have more than one. What's going on the other side of the equal sign? Mass times final velocity in y. Remember, I'm kind of doing this. Think about this. I'm doing this, right? What's that pure doing in y right now? How fast is it going in y? It's going nothing in y. Now it's going in x. But we're talking about y here. So notice that's not obvious. That final velocity in y is the same as it was at the start. It's not moving in y. That's exactly right. So that's 0. So the whole right side 0. Am I happy with this equation? I'm not happy. I mean, it's right, but I'm not happy because it's got 2 unknowns in it. So bummer. Maybe if I go to horizontal, maybe there'll be the same 2 unknowns and I'll be able to solve it. Or maybe I should have started with the horizontal one because it only has 1 unknown. I don't know. Again, I think this is a good illustration because this is hard. I mean, this feels hard to me. And the other thing is like, you know, if I gave a genuine final exam in this class, I'm not sure if I could pass it. Because like we already did this problem using other methods. And if you just get turned loose in the real world with a random problem, you don't even know what section it's in, so to speak. And this is why people think this stuff is hard. It's really difficult to think these things through. So these equations, the one thing I want you to take away is these equations are all made from each other, you know, and so you can, if you look at the large, you know, you leave a class like this and you have this 3 pages of notes in this class that I made that are all typed and it's like as tight as you could possibly get, it's still 3 pages. You know, you could actually use kind of any of them. Maybe some of them are easier than others, but you know, to actually understand it, you just have to kind of play with everything, and you know, it would take way longer than it should. But it's like that's what I'd have to do. Taught this class 5 times now, and it's like that's still what I would have to do. So let's see, what about horizontal then? What happens there? Well, I still have a mass times initial velocity, but this time we're talking about x. I've got maybe some forces in x, maybe a whole bunch of them. I don't know. So maybe a whole bunch of impulses, and same as before, I have a final velocity in x. And so what do I know about this? Well, so again, I'm assuming I started from rest. And so this is still 0. In the previous one, I didn't really have to think about it being at rest. At the time I was, but the fact that it stays on the ground, it didn't really matter if it was at rest. It just isn't moving in the y, right? So the arrest comment really belongs down there because I wasn't moving in the X at all. So, and then notice this is like, what force does he have to pull at to reach a speed of 12 meters a second? Notice there actually is a place for that 12 to go now, which means my mass has got to go somewhere. This time I'm glad it's metric, right? Because I just get to put 32 there. I don't have to divide like I did a minute ago for the pound problem. I can just stick 32 in there. That's really cool. And so then what do I have for forces? Well, oh, I got that force of friction going backwards, right? So that's a negative force of friction, which I don't know what it is. I'll just leave it at that for now. Times some time. Oh, wait, isn't the time just 8 seconds again? It's always 8, right? Everything's 8 seconds. So there's that. And then he's pulling to the right with whatever that force is. But again, it's got to be modified by the cosine of 38. So there's 2 impulses. So all this stuff applies to the skiers and all the stuff we've done. It's how much force and how much time. I can do these problems with impulses and momentum. So I don't like that because it's got 2 unknowns in it already right there that I don't know. And then at least on the other side, I've got a number, whatever the heck that is, 32 times 12. It's 384. So I'm not happy with that one either. And I'm even less happy than I was before because it isn't even the same 2 unknowns. But
Force of friction.
what do we know?
Force of friction is equal to the normal ground times the
Yeah.
coefficient of friction.
Weren't those 2 things related? Like how much normal force pushed on you made an effect on gravity, right? If this chair weighs a lot, it's not going to want to slide as well, right? So fortunately, I can actually convert that out of there. I can make it so that there's only one, so that there's 2 unknowns. So let's see, what was it? Was this it? Force of friction. I'm thinking out loud here, I'm not sure I remember. You take the normal force times the friction force. So since that friction force we're told is 0.1, then I could actually convert the force of friction out and just say normal times 0.1 instead. Does that make sense? So I can say, oh yeah, that can be rewritten as the normal of gravity. And I'll write 0.1 in front of it. And I guess the negative sign is still there. So it's like, oh, okay, cool. Now I actually have 2 equations, 2 unknowns. So actually I'm going to be able to solve this. And then I'll know forces and gravity. I'll sort of know everything once I figure that out. Again, I remember what the question was that I was being asked, but so in the interest of time, I would typically throw this one into a matrix because this is a nice looking 2x3 matrix. Notice the N's and F's are not squared. So it's linear for any of you who are taking linear algebra. So if I put this in the matrix, I get the normal of gravity is 256 newtons. Again, take a look at this number here. Gravity was pulling down at 314. Do you see how it came out less? Why did it come out less? Because I was pulling up on it some. So ground didn't have to do near as much work because I was lifting part of it. Does that feel good? I don't know that it's right, but the fact that it's less than 314 does make sense. And then the force I would have to pull to bring all of this about would be 93.4 newtons. Now, that's a dumb illustration. It's like, why would somebody pulling a kayak along the grass want to make all these calculations? But, think of it in terms of a car. Somebody's got a dragster and they're trying to get it to go down the track really fast. They want to, get it done in 8 seconds. They want to reach a speed of a certain speed. It's a certain weight. Being able to figure out how much force the engine has to create to be able to make that happen. That's realistic. This is sort of dumb, but it's at least something you can kind of touch and put your hands on. The fact that, there's a bit of an upward pull basically helped gravity have less of an effect, right? Or I'm sorry, helped friction. Friction wasn't as much of a problem as it would have been. Incidentally, I did that the other day coming out of that river, and it was just a terrible idea. Like, I usually just carry my boat on my shoulder, but it's like, it's nice not to have to carry it. It's on the ground, I'll just drag it. But it dragging through the dirt was so stinking much work. It was like, that's a stupid idea. I'm never doing that again. So again, you kind of need to soak on these things. Carrying a loaded kayak is not cool. Dragging it is not cool as well. Okay, let's do some really cool problems now that. Let's see. Shoot, I don't have time. Which one should I do? Don't have a choice. Look at 1539. We're not going to get done, but I'll do this one and then we'll do the other one tomorrow. Whatever. So I've asked a few people about this to see if this is actually a thing, like, but I don't know if you've ever shot much. I've shot just a little bit, but one of the things that happens when you buy a bull is it'll tell you the muzzle velocity, like this is 1,400 feet per second. You shoot this bullet, it's 1,800 feet per second. It's like, how do you know that? I mean, you can't really clock that. So supposedly this is a trick that allows you to do that. Do you know anything about it?
Clocking feet per second.
What?
Clocking the feet per second.
Yeah. Can you
Yeah.
shoot like a,
Yeah, there's things that put the barrel through. I forget what it's called. It clocks the.
like a cop does with a radar gun? It'll radar the speed.
It's called, I've used one before. You stick the muzzle of the barrel through it and you shoot the gun and it tells you the feet per second.
Is it because it hits something on the other end that it's kind of like a scale based on how far it pushed it or something like that? However that works, does it make sense? It would be the topic we're studying. Like even if it was like you put it in a tube, shoot it, it hits a plate at the end and the plate, well, that's an impact, right? And so the fact that, what's it called?
Chronograph.
Chronograph.
Chronograph. So it obviously has something to do with time.
Yeah. So does it make sense like why what we're studying would kind of figure into that? So I can know how much it weighs. That's not hard. I can weigh the lead slug before I shoot it in there. I can know what it weighs. And then if I know how much time it takes to kind of come to a stop, and I can see how that invention would exist. But anyway, let's take a look at this because this is sort of the old school version of this. Take a look at your note sheet really quick. Because what we're jumping in here to now is conservation of momentum. The fact that momentum is actually conserved. In other words, if you have an initial amount of momentum, you're going to have the same amount later on, just like energy was conserved. So we had kinetic energy, initial kinetic plus initial kinetic potential, and then it was going to be the same later on, energy would be conserved. Well, the same thing is true for conservation of momentum. Notice this is good for collisions when the objects stick together. In other words, the bullet is going to go into the wood, which means now it weighs more than it weighed before. Usually car crashes aren't this because it's like one or two football players. They're not going to stick together and move as one. They're going to bounce off each other in some way. And we'll be next studying impact where you can actually figure out where they're going to go. If they ram into each other, we can figure out who's going to go where and how fast they're going and all that, which is the note right below that. It says impact. So this is a kind of a cool one. So notice the equation, it says mv1 plus mv2. Well, that's the momentum of two different things that are about to impact each other. So one football player has a certain amount of momentum, the other one has a certain amount of momentum, they're going to bang into each other. In this case, it's going to be a bullet, which has a certain amount of momentum. Now the bullet has light mass, but a lot of speed. So its momentum will be coming from its speed. The block might weigh a lot, but it won't have much speed. It's sitting still, won't have any speed at all. So it's like these two things are separate right now, and they have a certain amount of momentum each individually. Well, they're about to become one. And of course, what's basically going to happen is you got this bullet with a ton of speed. It's going to hit the block, and then the block's going to move, but it's not going to move that much. Does that make sense? Because it's so massive, has a lot of weight relative to the bullet, so it's just going to move a little bit. And so notice over here on the other side, you've got the mass of the bullet and the mass of the block added together, and then together they're still going to have the same momentum they started with, but then we're going to be able to figure out that velocity or something of that nature. Does that concept make sense? So let's quickly, in the interest of your valuable time, see if we can pull this off. Let's see. So I've got mass of the bullet times the velocity of the bullet plus the mass. What am I going to call that other thing? Block. I guess I'll say wood. Mass of the wood and the velocity of the wood, and that's going to be equal to the mass of the bullet plus the mass of the wood times the velocity of both of them. I'll just leave it V, I guess.
Maybe find the velocity.
Yeah, so let's see, what do I know? So this is the equation. Again, it's got 1, 2, 3, 4, 5 unknowns. And so I don't like this equation right now. So yeah, I got to know some things. Hey, the wood weighs 4 kilograms. Okay, there's something I know. So the mass of the wood is 4 kilograms. And the block, the original block of wood, its velocity is at rest. And so I know that. I know that the block isn't actually moving. That kind of makes sense. The bullet is 2 grams. Ooh, grams. One was grams, one was kilograms. That's not good. Do I care? I care. Should I switch that 4 to 4,000 and do this in grams? Or is it better to be in kilograms? Yeah, it doesn't matter, but we can't ignore the fact that they're different. I'm thinking kilograms because kilograms is a part of newtons. And if I need force, I'm looking at this going, oh, well, there isn't a force. I'm not really sure. I'm used to kilograms, and so I don't know. I'm not really sure which one to pick. I don't really like, if I change 2 to kilograms, what do I have to do to 2? Yeah, kilo is 1,000, so this is just 1, so I'd be dividing by 1,000, so I'd move the decimal point 3 places to the left, so wouldn't the mass of the bullet then be 0.002 if I decided to go kilograms with it? I think that's right. So yeah, I know quite a bit of stuff. But notice I still have, at least at this point, I'm just kind of taking stock of where I am. I got 2 unknowns, and so I still don't like this equation, at least right now, but maybe I just haven't read the rest of the problem. I don't know. It swings upward to maximum. So it's like, oh darn, they're not telling me either of those. They're not telling me the velocity of the block. They're not telling me anything else. But then there's all this stuff about the block moving, right? Like, why are they, what's that all about? Again, this is like the caveman version of the modern chronograph. Is that what you called it? Chronograph?
Yeah.
This is like the caveman version of how to figure out how fast the bullet's going. But notice this is just like, well, the kayaker that fell off the 25-foot cliff. Like here, if you know how high it went working against gravity, then does it make sense you might be able to work your way to getting a velocity somehow? Or so it's not as nice as I would like to have had it, but maybe I can use that to figure, I don't know, something out. So in the interest of time, because I want to get you out of here, for a lot of the problems we did before, we used this equation: velocity squared equals the mass times acceleration times the distance. It was S minus S0, but we used that equation for quite a few things. So let's see, what do I know about this? Well, I know the mass of the block and the bullet. Do you agree that's the block and the bullet? So this is 4.002. Do you agree with that? And I know the acceleration of gravity in the vertical direction because I'm metric is 9.81. And then the distance has to be in the same direction vertically. So how high did it go?
The block or the bullet, or both?
So they told us that's 6 degrees, right? And the string that it was hanging on is 1.25. So that makes a right triangle right there. So sine would give me this length right here, but I don't really want that one. I want the height. I need a height. So if I take 1.25 times the cosine of 6, I get 1.243. Does it make sense? That's how tall that is. So if that's the case, then how much did it lift up? How much did that lift the block in a vertical direction? Remember, it used to be when it was hanging straight, 1.25, right? So if I take that minus 1.25, then it lifted it 0.0068. Rounding that off. So I can actually determine my velocity. Now, again, that was kind of the shortcut way. I could use the same S of Y type equation, the longer version that I did with the kayaker a minute ago. But this is what I had you using for those 2 skier projects, that kind of shortcut equation. So let's see, 4.002 times 9.81 times 0.0068. I got 0.2669. If I take the square root of that, that doesn't make sense. 0.5. What did I do wrong? 0.5. That's exactly right. So if I have this bullet that has very little mass, but a lot of speed, and it hits a block, is the block going to move really fast? No, the block's not going to move very fast. Does that make sense? So my first thought was that doesn't make sense. That's too small. But after I thought about it, I thought, well, actually, it does make sense because the block's not going to move very fast. It's pretty massive, right? Cool. So if I throw that in there, you see how now I could actually figure out, just based on this alone with the initial, like caveman style, I could figure out the initial velocity of the bullet. Isn't that kind of cool? So that's why this thing's called a ballistic pendulum. That's kind of neat, isn't it? So let's see, times 4 times 0.002, and then divided by 0.002. Oops, I did that wrong. 2 times 4. There we go. Divide by 0.002. I think I got this. It's not the same answer I've got sitting on my note sheet, but so I'm a little worried I did something wrong. Wow. So 1,034 meters per second. That's pretty cool.
Doesn't this all depend on,
I'm sorry?
doesn't this all depend on like the object's ability to actually catch the bullet? Because I'm thinking of like, if you were to shoot it like a little bit of can, like I've shot a little can so many times, the bullet goes through it, the can like doesn't move.
That's exactly right. Yeah.
So in that case, would we only be looking at like the mass of the specific spot where the bullet's gonna hit?
Yeah, it's a super good question. Yeah, because it's weird that the can maybe not doesn't even move. Think of it as like a football player running into somebody stationary. You imagine that would be like, you know, they crash on the ground, but it's like it got through it so quickly. That seems complicated.
Steel plate. Not any wood, right?
That's the
So incidentally, just as a side note, and then I'll shut up, but that number 0.0068 over there, when I did this problem before, I rounded it to 0.007. That kind of feels like an okay thing to do, right? If you did that on a test, if you call that 0.007, that'd be fine, right? I did the same problem and I got 740 meters a second as a result of that. So I thought I was doing it wrong because I was looking at my notes like, what's going on? But it changed the time here from 0.52 seconds to 0.37 seconds. That's a very profound percentage change. And so isn't that kind of weird how rounding made such a large difference in this case? And it kind of makes me think maybe I should have even kept more of that 0.0068 if I actually really wanted to know what this was. This is kind of neat because it's like you could have a cell phone and take a time lapse shot of it and actually be able to take these measurements. Because of course, that's nice to draw that little nifty picture there, but how are you supposed to capture that? I do think there is some kind of a, I'm making this up, but I have a feeling there is some kind of a gauge or something that sits above this and it like pushes it up and then it lets go and the gauge stays at the height that was at before. So you wouldn't have to have a, because obviously in this era, they didn't have cell phones or things of that nature. If you're using a block of wood to figure out the velocity, you're going Fred Flintstone style. So maybe there could be some kind of a something on the back that it pushed it this way. And then when it left, you know, it's like, oh, okay, I know how far it pushed it. Now I can take measurements. And of course they swung this thing, right? They swung it because there's very little friction there. If they had it on a table and shot and it slid down the table, then you'd have to figure out the friction coefficient of the wood on the table and, you know, some of those kind of things. It'd be hard, right? So I hope we have time to tackle this tomorrow because this is just a wonderful question, but just look at it before you go out the door. I've got a video of this, but you see what's going on there? It's like a, so this is an example of what impact would do. If you shoot a bullet and you're on a skateboard, then you're going to go backwards. Instead of absorbing the recoil with the friction you have on the ground, you're actually going to go backwards. And it's kind of cool because you can tell that's an AR and he doesn't just shoot like one bullet. It's like shoots like 50 of them and he just starts hauling backwards, which seems like a good idea to me, despite the fact that that could be a bad idea. Anyway, that's good enough for now. Take a break and we'll talk more about this later.